What we see here is the upper portion of a Fisher Leveltrol level measurement device, just the upper portion of it. This is a displacement type level transducer used to measure liquid level interfaces, and also liquid density. It's a pneumatic instrument. In this particular model, there are no electronic parts, no electrical components at all. It's all a pneumatic mechanical mechanism. What we see here is the top assembly of what would normally be a cage. Below this flange would be a matching flange going down to a section of pipe that would hold the liquid level to be measured. Or, alternatively, this flange could be bolted directly to the top of a vessel holding liquid. Coming down out of this assembly would be a rod, at the end of which would hang the displacer. As the liquid comes up around the body of the displacer, it creates a buoyant force that pushes in the upward direction. The result of that buoyant force is that the apparent weight of the displacer decreases. As water, or whatever the liquid is, rises up, the buoyant force becomes greater, and that causes the displacer to appear to weigh less. The weight of the displacer is suspended by a lever on the inside of this nozzle. Of course, you can't see it. This is solid metal. If you look in the top here, you can see a little rod sticking out with a little ball-shaped end, and that is where the attachment would hook onto, comes down to the actual displacer. That lever comes over here. It rests against a knife-edge support and then attaches to something called a torque tube. A torque tube is a hollow tube of springy steel, and the idea is that when you apply a weight to the end of that lever, it creates a torque on the length of that torque tube, causing it to twist. Now, the torque tube is hollow for most of its length, but it is sealed off at the end, so process pressure fluid cannot make it through here and leak through the torque tube out into the head of the instrument. What can happen, though, is at the end of the torque tube, there's a small solid rod that goes in through that long hole in the tube and is welded to the blind end of that hole. The idea is when there's weight applied to that lever, it twists the torque tube. That torsional force is weight or force is borne by the length of that tube. It's a torsional spring. This solid rod, since it attaches to the far end of that tube and is welded to the end, that rod rotates as the torque tube twists. So the purpose of the small rod is to transfer the twisting motion of the torque tube at the far end, at the process end, transfer that motion over here where it may be measured. To give you a demonstration, I'm going to take a screwdriver. I'm going to use the screwdriver to push down on the end of that lever that we saw just a moment ago. So here's the lever. I'm going to take the screwdriver, rest it on the end, and now I'll be able to push it down. So when I push down that screwdriver, I'm now simulating weight at the end of that torque tube lever. And I can feel the springiness of the lever as I push down. It wants to return. If I look over here at the head of the instrument, you can see a slight motion between the baffle and the nozzle as I push down on that lever. As I push down the lever, which is simulating more weight on the displacer, the baffle approaches the nozzle, and that builds up a back pressure which will be amplified into a 3 to 15 psi pneumatic signal. As I release weight on the end of the lever, the torque tube relaxes, it turns clockwise from our perspective, and the baffle backs away from the nozzle. So the idea here is we have a motion balance system. That nozzle is trying to maintain a constant gap between itself and the baffle. As the baffle rotates with the twisting of the torque tube, that nozzle maintains a constant gap and it must flex with it. Now the nozzle itself is a little bit interesting. We have a very special board-on tube here that has a tiny pilot hole for the nozzle. It goes all the way through, a tube within a tube, comes back here to a connection. So this board-on tube is like any other board-on tube in that you could fill it up with an air pressure and it will expand and flex and try to straighten out. But it also has a tube within the board-on tube sending a small amount of air to the end of the nozzle. This is a very special board-on tube assembly. So as the baffle approaches and retracts from the nozzle, the back pressure of that nozzle is fed back through that tube inside of a tube, comes over here, ends up being amplified. And then that tube will expand or contract as necessary by the feedback mechanism to keep a constant gap between the flapper and the nozzle, the baffle and the nozzle. So it's somewhat of a complex mechanism. There's a lot going on here. It's not obvious from first inspection. Probably the most complicated or confusing part is the torque tube itself, which I've tried to explain. A long, skinny tube of springy steel, sealed and welded at the end, so that process fluid cannot leak through the length of the torque tube. The torque tube acts as a spring and a mechanism to transfer the motion, the rotary motion of that lever, all the way through to the front where it can be sensed.